Yes, students, as we have discussed, if A bar is equal to A1I, A2Z, A3K, B bar is equal to B1I, B2Z, B3K, C bar is equal to C1I, C2Z, C3K, then box of A bar, B bar, C bar can be written as A1, A2, A3, B1, B2, B3, C1, C2, C3. Now, when the vectors are expressed in terms of Ijk, you can write box of ABC is equal to that contain the coefficients of Ijk. If the vectors are given other than the Ijk, then you have to express in a different way. What is that? First one is, if A bar is equal to A1 into L bar, A2 into M bar, A3 into N bar, B bar is equal to B1 into L bar, B2 into M bar, B3 into N bar, C bar is equal to C1 into L bar, C2 into M bar, C3 into N bar. Then box of A bar, B bar, C bar is equal to, this is A1, A2, A3, B1, B2, B3, C1, C2, C3 into box of L bar, N bar. So then why you are not written here Ijk? If you want, you can write by using this. If you want, you can write Ijk, but box of Ijk is equal to 1. How? Why? So if I go for this one is, I can write box of Ijk as I dot of j cross k. We know it from the definition of cross product. J cross k is equal to I. It's I dot I is equal to what? 1. So therefore, hereafter, whenever the vectors are given in terms of Ijk, no need to write a det into box of Ijk because box of Ijk is equal to 1. If it is other than Ijk, you are supposed to express as what? Whatever the vectors are given expressed in terms of L bar, M bar, N bar, that has to come as a product of the determinant into box of L bar, M bar, N bar. Let us see how it is. The proof of this one is, I go for B bar cross C bar. As we have discussed earlier, B cross C bar other than what? Ijk. I can write M bar cross N bar. Next, N bar cross L bar. Next, L bar cross M bar. You write down B bar coefficients B1, it's a B2, it's a B3. Next, C1, it's a C2, it's a C3. Followed? Now you expand it. This gives us M bar cross N bar into AD minus BC, B2C3 minus B3C2 minus N bar cross L bar, N bar cross L bar. Now this into this, now this into this. B1C3, B1C3 minus B3C1 plus L cross M into, yes, now you leave this column, this row, I can write B1C2 minus B2C1. Now I will write this one as, this you got it. Instead of minus, you take minus inside, I can also write M bar cross N bar, B2C3 minus B3C2, yes, plus N cross L into B3C1 minus B3, okay, B3C1, here N cross L into B1C3, it's a B1C3, right, B1C3, B, that is B1C3, plus L bar cross M bar into B1C2 minus B2C1. Followed? Now I take dot product of B bar cross C bar. Take the dot product of A bar here on both sides. Now I can write A into L1, A1 into L bar, plus A2 into M bar, next A3 into N bar, dot, I can write B2C3 minus B3C2 plus N bar cross L bar into, yes, B3C1 minus B1C3, next L bar cross M bar into B1C2 minus B2C1, right, B2C1. Now take the dot product of this into this, this into this, this into this. Now, so A1 L bar, I can write this one as, I can also write this dot with this one, this dot with this one, this dot with this one. So as we have shown already, what we have shown, if A bar is equal to A1I plus A2J A3K, B bar is equal to B1I plus B2J plus B3K, C bar is equal to C1I plus C2J plus C3K, we have expressed as a determinant. Means scalar triple product is nothing but a what? Box of ABC, is nothing but a what? Determinant. What are the properties you are going to apply in the what? Determinants? All the properties shall also be extended to what? Box of ABC. In a determinant, if two rows or columns are identical, the value of the determinant is equal to what? 0. Meanwhile, in the box product, if two vectors are same, we can write that is equal to what? 0. Because box of ABC is equal to A1, A2, A3. It's a B1, B2, B3. It's a C1, C2, C3. We know it already. So therefore, in the same fashion, we can also write box of AAB means what? Two rows are same, therefore is equal to what? 0. I can also write box of ABB is equal to what? 0. I can also write box of ACC is also equal to 0. Hereafter, not only in what? Box product, but even in what? Scalar triple product, if two vectors are what? Repeated, its value is equal to what? 0. Why? Scalar triple product is nothing but a what? Real number. It may be positive, it may be negative, it may be what? 0. So therefore, now you take the dot product of A1 into L bar dot with this one. So therefore, I can write A1 into B2C3 B3C2 B3C2, that is L dot of M cross N, means I can write box of L bar, M bar, N bar. Next, if I take this dot product with this one, that is L bar dot of N cross L, two vectors are same as it is, its value is 0. This with dot is 0. This with this is what? Is also 0. Because L is there, here also L is there. Next, if you go for A2 into M bar, if you take a dot product, this is also 0. Now this is also 0, only comes here. What happens now? Box of LMN into bracket, whatever is there, you take A2 into B3C1 minus B1C3. Next, similarly, A3 into N, this is also 0, this is also 0, only this comes with this one. I can write box of LMN, box of L bar, M bar, N bar into A3 into B1C2 minus B2C1. So therefore, I can write this is same as the determinant This is A1, A2, A3. It's a B1, B2, B3. It's a C1, C2, C3 into box of L bar, M bar, N bar. Box of L bar, M bar, N bar. So therefore, hereafter, whenever the given vectors are expressed in terms of L bar, M bar, N bar, other than Isaac, you can write the box of ABC is equal to determinant A1, A2, A3, B1, B2, B3, C1, C2, C3 into box of L bar, M bar, N bar. Right? Note, if A bar is equal to 0 or B bar is equal to 0 or C bar is equal to 0, then box of A bar, B bar, C bar is equal to 0. In a box product, in scalar triple product, if any one vector is what? Null vector, then total det value is equal to what? 0. Why? In a determinant, if the elements of any row or a column all are equal to 0, then the value of the determinant is equal to what? 0. In the same fashion, scalar triple product is nothing but a determinant. So therefore, in a box product or a scalar triple product, if any one vector is a null vector, the value of the box is equal to what? 0. Let us discuss about note 2. If any two vectors parallel or collinear, parallel, then A bar, B bar, C bar is equal to 0. Any two vectors means what? Among A bar, B bar, C bar. Followed? Right. Next, third one is, as I told, the box product scalar triple product is nothing but determinant. In a determinant, the vectors in a determinant, the elements of a row or a column are interchanged only in two rows or in two columns. The value of the determinant is unaltered, but sign changes. Here also, in a scalar triple product, if the dot and the cross are interchangeable in a cyclic order, vectors can be interchangeable in a cyclic order. Without a cyclic order, sign changes but value is unaltered. So therefore, what I do is, I can write B, C, A. Next, C, A, B. Now in a determinant, if 3 rows or 3 columns are interchanged, minus comes 2 times, minus of minus plus. If 2 rows or columns are interchanged, the value of the determinant is unaltered, but sign changes. Here also, you see, now the vectors can be interchangeable in a cyclic order. So therefore, I can write A dot of B cross C is same as B dot of C cross A is same as C dot of A cross B. What you have observed is, this came written either this way or this way or this way. Why? Because the vectors are interchanged in a cyclic order. Dot and cross are interchangeable in a cyclic order. This is the most valid property one has to take into considerations. So therefore, here dot, here it's a cross, here a cross, here it's a what? Dot. Dot and cross are interchangeable in a cyclic order. Without the cyclic order, sign changes. You see, I will write this one as minus ACB minus BAC, right? Minus, I can write minus CBA, right? After A, After A, B, C, next B, C, A, next C, A, B. When they are interchanged in a cyclic order, the sign is what? Unaltered. Without the cyclic order, the sign changes. So therefore, next comes about fourth property. This is A bar plus B bar, C bar, D bar. Yes, box product is nothing but a determinant. In a determinant, if the elements of row or a column is a sum of two determinants, then that determinant can be expressed as sum of two determinants, right? Now A plus B, I can write A bar, C bar, D bar. Next, B bar, C bar, D bar, right? A bar, C bar, D bar, B bar, C bar, D bar. Now coming this one is, next one is, I go for A bar plus B bar, next C bar plus D bar. I can write D bar also. It makes no difference. Now, for the first vector, A bar, this is C bar plus D bar, D bar. Next, I can write B bar. This is C bar plus D bar. It's a D bar. Next, taking this as a separate what common expansion, A bar, C bar, D bar. Next, A bar, D bar, D bar. Plus, next B bar, that is C bar, D bar. Next, B bar, that is B bar, D bar, D bar. So now, here two vectors are repeated. Its value is 0. Here two vectors are repeated. Its value is 0. Ultimately, I can write A bar, C bar, D bar, right? Next, B bar, C bar, D bar. With this concept, what we understood is, in a box product, if any vector is a sum of two vectors, then that box can be expressed as sum of two boxes. Okay, in box product we come across many properties. In a box product, vectors can be interchangeable in a cyclic order, means dot and cross are interchangeable in a cyclic order. Without the order, the sign changes, right? Next, in a box product, if two vectors are identical, then the value of the box product is equal to what? 0. In a box product, it's if any vector is sum of two vectors, then that box can be written as sum of two boxes. Sum of two boxes. Now, as we have discussed just now, if A bar is expressed in terms of L bar, M bar, N bar, B bar also, C bar also. Let us recall the definition by giving one vivid example as a decide. Now let that is P bar is equal to 2A bar, 3B bar, 4C bar. Next, Q bar is equal to A bar minus B bar plus C bar. R bar is equal to A bar plus 3B bar minus 4C bar. Then box of A bar, B bar, C bar. Yes, let us see what is box of A, B, C. Is nothing but det coefficients of A bar, B bar, C bar. 2, 3, 4. 1 minus 1, 1. That is 1, 3 minus 4 into box of A bar, B bar, C bar. Expand this. This is 4 minus 3 into minus 4 minus 1 plus 4 into 3 plus 1. Yes, now this is nothing but into box of A bar, B bar, C bar. Expand this. 2 into 1. Next 5. It's a 15. Next 4. 16 into what? Box of A, B, C. Now I can write this one as, now 2 plus, it's what? 31. That is 33. I can write box of A bar, B bar, C bar. That's right. Box of A bar, B bar, C bar. After knowing the what? Expansion of scalar triple product by using determinant method, let us have still more application of box product. What is that is? If A bar is equal to, I take A1i, A to A1i plus A to Z A to Z plus A3K. B bar is equal to B1I, B2Z, B3K. C bar is equal to C1I, C2Z, C3K, right? C3K. Next, L bar is equal to L1I, L2Z, L3K. Next, M bar is equal to M1I plus M2Z, this is M3K. N bar is equal to N1I, N2Z, N3K, right? Then I want box of A bar, B bar, C bar into L bar, M bar, N bar, right? Now I can write this one as, this is A1, A2, A3, B1, B2, B3, right? C1, C2, C3. This is nothing but L1, L2, L3. This is M1, M2, M3, N1, N2, N3, right? Okay, now these are in terms of Ijk, box of Ijk is equal to what? 1. Now remember, now I have to multiply one determinant with another determinant. Every determinant is nothing but a square matrix. So therefore, in matrices, any two matrices are said to be multiplied provided the number of columns in the first matrix must be equal to number of rows in the second matrix. Followed? So therefore, number of columns in the first matrix must be equal to number of rows in the second matrix. So therefore, now in matrices, you can multiply row with a column or a column with row. Whereas in det, no restriction. You can multiply row with a column, column with a row, row with a row. These are the things, column with a column also. So therefore, when you are multiplying row with a row, you are not multiplying row with row in the second matrix. You are multiplying row with its column in its transpose. That's the concept behind it. So therefore, that we are not taking into us consideration. Directly we are going for row with a row. So therefore, multiply first row with first row. I can write determinant, yes, come on, A1, L1. Come on, A2, L2, this is A3, L3, first row with this one. Next, first row with second row, this is A1, M1, A2, M2, this is A3, M3, right? Next, A1, N1, A2, N2, A3, N3. Next, now second row with first row, yes, B1, L1, B2, L2, B3, L3, next B1, N1, B1, M1, B2, M2, B3, M3, next B1, N1, B2, N2, B3, N3, right? Next, I can write C1, L1, C2, L2, C3, L3, C1, M1, C2, M2, C3, M3, C1, L, that is N1, C1, N1, C2, N2, C3, N3, right? This is nothing but A bar dot L bar, A bar dot M bar, A bar dot N bar, B bar dot L bar, B bar dot M bar, N bar, C bar dot L bar, C bar dot M bar, C bar dot N bar. So therefore, this is nothing but box of A, B, C into box of L bar, M bar, N bar. Followed? Now, on all this, you have much applications in Scalor Triple Product correlating to what? Volume of a parallelepiped, volume of a tetrahedron. You can find out many things on this. We shall discuss in the sequel. Now what I want is, next one I want it. I want box of ABC whole square. Box of ABC whole square. Now from this one, what I can write is box of ABC into box of ABC into box of ABC, right? Now this is nothing but, yes, that is in place of L, M, N, I am taking A, B, C. Why to write time wasted is? I want box of ABC whole square. As I have given box of ABC into LMN, in place of LMN you take A. So A dot A, next A dot B, next A dot C, next in place of A, B dot A, next B dot B, next B dot C, next C dot A, it's a C dot B, C dot C. This is the value for what? Box of ABC whole square. Box of ABC whole square. Let us see the application on this. Okay? The application of that concept of what box of ABC whole square is equal to that A dot A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B, C dot C. Let us see. If A bar, B bar, C bar be three unit vectors which are equally inclined to each other, which are equally each other, then box of ABC whole square is equal to dash. It's an extension of that concept. What is that? Yes, given A bar, B bar, C bar are three unit vectors then mod A is equal to mod B is equal to mod C is equal to 1, which implies A dot A, B dot B, C dot C is equal to 1. Given A bar, B bar, C bar are equally inclined to each other, which implies angle between A bar, B bar is equal to theta is equal to B bar, C bar, next is equal to C bar, A bar. Means, which implies A dot B is equal to mod A mod B cos theta is nothing but cos theta. Meanwhile, B bar dot C bar is equal to mod B mod C into cos theta is equal to cos theta. C bar dot A bar is equal to mod C into mod A into cos theta. So therefore, this is nothing but cos theta. Is nothing but what? Cos theta. So therefore, A dot B is equal to cos theta, B dot C is equal to cos theta, C dot A is equal to what? Cos theta. Followed? Now with this one, box of A, B, C, as you know already, this is nothing but A dot A, A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B, C dot C. So therefore, substitute the what relevant values in that determinant. We get this one as A dot A 1, this is cos theta, this is what cos theta. Now this is cos theta, this is 1, this is cos theta, this is what cos theta, this is cos theta, this is the 1. So therefore, this is the value of box of ABC whole square when A bar, B bar, C bar are the three vectors, or we can call it as lines, which are equally inclined to each other. Then the condition is dash. Sometimes he asks, if three lines which are equally inclined to each other, then the maximum value of that angle is dash. If you expand that, you are going to get some value of what? Cos theta. Some value of what? Cos theta. That you have to find out according to its range, because cos value always lies between what? -1 and +1. So therefore, whenever the three vectors or three lines are equally inclined to each other, then box of ABC whole square. If they give three lines, take them as what? Vectors. First line is L1 is a bar, L2 is what? B bar, L3 is what? C bar. Because of what? Generality, because of easiness, take them as what? Unit vectors. Then you get what? A dot A, B dot B, C dot C is equal to 1. And given A bar, B bar, C bar are equally inclined to each other, then angle between A bar, B bar is equal to theta, B bar, C bar is equal to theta, C bar, A bar is equal to what? Theta. So therefore, now A dot B is equal to cos theta, B dot C is equal to cos theta, C dot E is equal to cos theta, because they are unit vectors. Then substitute the corresponding. This is the value of what? Box of ABC. Let us recall the what? The definition of box of ABC whole square is equal to what? Determinant A dot A dot B, A dot C, B dot A, B dot C, B dot B, B dot C, C dot A, C dot B, C dot C. Still for what? The higher concept. Now if I go for this one is, if V is the volume of a parallelepiped with coterminous edges, A bar, B bar, C bar, then the volume of parallelepiped with the edges alpha bar is equal to A dot A into A bar, A dot A into A bar plus A dot B into B bar, A dot C into C bar. Next, beta bar is equal to A dot B into A bar, B dot B into B bar, B dot C into C bar. Gamma bar is equal to A dot C into A bar, B dot C into B bar, C dot C into C bar. Now let us see the proof of this one is very simple. V is the volume of a parallelepiped with the coterminous edges A bar, B bar, C bar. V is equal to volume of parallelepiped with edges A bar, B bar, C bar. which implies V is equal to box of ABC. Now I want to find out V1 is equal to volume of parallelepiped with edges alpha bar comma beta bar comma gamma bar is equal to box of alpha beta gamma. But the vectors are in terms of A bar, B bar, C bar. Det into box of ABC you are supposed to write. If it is IJK, no need to write box of det into box of IJK. But box of IJK is equal to what? 1. So therefore, now what I can write is V1 is equal to determinant. What's the quotient of A bar? That is A dot A. Next, A dot B. Next, A dot C. Next, yes, come on, A dot B. Next, B dot B. Next, B dot C. C dot A. C dot B. C dot C. Into box of ABC. Why box of ABC? The vectors are given in terms of A bar, B bar, C bar. I can write, yes, V is equal to, this value we know it already. I can write V1 is equal to, this is nothing but box of ABC whole square. Already another one is a box of ABC. So therefore, V1 is equal to box of ABC whole cube. So therefore, V1 is equal to what? V cube. This is nothing but the volume of the what? Parallelepiped formed by the vectors alpha bar, beta bar, gamma bar, when they are expressed in terms of what? A bar, B bar, C bar, that too under the definition of box of ABC whole square is equal to determinant A dot A, A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B, C dot C.